I think we're going to do it, huh? Good afternoon. The last time we spoke about the hydrogen atom and its electron. And we know now that the electron of the hydrogen atom behaves like a wave, and we can determine the energy that these wave functions have. There's a whole bunch of energies as we have determined. And one of the dilemma we have is if we know a wave, as you see, the electron can behave as a wave and as a particle. And it's sort of mutually exclusive to some extent. And if we know the wavelengths very well, we can really draw or construct the probability distribution of that electron because we know the wavelengths. The wavelength is lambda, so it can be here, it can be here, it can be here. It can be not there where it goes through zero, okay? But everywhere else, there's high probability to find it here, high probability to find it here, high probability to find it here. This doesn't really help us, okay? Because we would like to know where it is. But this is the dilemma we are in. If we know the wavelengths very well, we know the momentum. We can describe this with one single wave. Now, on the other hand, if you want to know exactly or to some certainty where that electron is, you need to make a wave function like this, where there you have this maximum here, so the probability to find it in here is very high and very small to find it somewhere here. But in order to mathematically construct something like this, you need a whole series, a whole bunch of wavelengths, and you have to sum them up, okay? So now that's the other dilemma. Now we know the position very well. Now we know the momentum not very well, okay? We know the position, but we don't know the wavelengths, essentially, because there are so many wavelengths in order to construct this mathematically. So this is what Heisenberg found out, and he said that the uncertainty in location, that means to finding that electron, times the uncertainty in momentum, this is nothing else but the uncertainty in velocity, because momentum is mass, and the mass is a constant, but the velocity changes, okay? The uncertainty in momentum or velocity, this product has to be a fixed number. It can't be smaller than a certain number, okay? It can be that certain number, but it can't be smaller. That's the uncertainty relationship, and this number is h, that's the number for the Planck's constant divided by 4 pi. So that's the Heisenberg's uncertainty relation. So if we want to know where it is exactly, we can't, okay? Because we have to have all these different wavelengths. So I then talked to you about the Schrödinger equation, and I probably lost quite a few of you, which is not a problem, because the Schrödinger equation, I just wanted to make sure that you have heard about this. The Schrödinger equation, this guy Schrödinger, what he did, he is one of the founders of quantum mechanics, and he said, now I describe the electron as waves, but I would like to find out what's the solution to this wave function. How many different wave functions can I have, and what kind of energy do these waves represent? So you can we had this one-dimensional box here. We had the electron going back and forth in one dimension. And so we said it has to be 0 here and it has to be 0 here. That we call x equals 0, and this is x equals L. That's the length of that. That's how this L gets in here. Not to really worry about it. So the electron definitely has to have kinetic energy while it's moving along. It has to have kinetic energy. And it has potential energy there where it's 0. It has the maximum of potential energy because it doesn't have kinetic energy. So, excuse me. Do is, we do a bunch of mathematical operations. There's some constants with that wave function. We say take the second derivative in the distance to dx squared, and these are constants. They are related to the electron, and what this says, we call these operations here, take the wave function and do something with it. And this is a operate with it. And we call this the Hamiltonian. An operator, it's just nothing but the mathematical instructions. If I define a Hamiltonian, so you got to do to this wave function these kind of operations, these mathematical operations. And what you get at the end, if you do this to that wave function, this operation here, you get the wave function itself and a whole bunch of different energies. Okay? So if you have certain wave function, then you have that energy, other wave function, and other energy, and so on and so on. This is essentially the quintessence of the Schrödinger equation, that you get these energy of this single electron in one-dimensional space. That's all there is to it. And it looked then, we call these energy levels, we call them orbital. But this is a one-dimensional orbital at the moment. We are not in 3 dimensions. We have this going back and forth in a box here. It's in 1 dimension, essentially. It goes in one direction only. So we call this n, that's the energy level. The lowest energy level can be 1. The energy, as we have seen, is not 0 because you can put half a wave in there in this simple case. So the energy of level 1 is just the ground level of the lowest possible energy level that the electron can have in this particular atom. All right? That's n equals 1. And so the energy of the nth level is minus the atomic number squared, Z squared, divided by the quantum number, or the level squared, times a constant, and that constant is called the Rydberg constant, and it's an energy. Because we want to get out energy, this definitely is not energy, so this are these constants that we had before, and this is an energy, and the constants here is 2.18 times 10 to the minus 18 joule. Joule is an energy unit. And if we do a whole mole of electrons, because it's kind of hard to have one electron only, we do a whole mole of electrons, then I have to multiply this with Avogadro's number, and I get 1,312 kilojoules per mole of electrons. All right? So what does this do? E equals, we're talking about hydrogen. E equals, n equals 1, so the energy level would be this here. Hydrogen has what atomic number? 1, so this minus 1 squared is still minus 1, divided by n equals 1, this is this here, 1 squared, so this is minus r infinity, okay, minus r, minus the Rydberg constant. So that is minus 2.18 times 10 to the minus 18 joule for 1 electron. That's the lowest energy state that electron in the hydrogen atom can have. Now let's go to level 2. 2 is, this is still 1 here because Z hasn't changed. And this is 1/4. It's minus 1/4. So the energy gets smaller, but the number is negative, so it increases essentially. Okay? So we have here 3 and so on. As you go further and further out away from the nucleus, these levels get much, much smaller, and we call this, they get so close to each other that it's a continuum. And why do we have this negative? That's a matter of definition. You can define your 0 anywhere you want. And the definition is, if that the nucleus is here and this electron is so far away from the nucleus that the nucleus doesn't have any influence on it anymore. Okay? It's gone. We call this the energy state 0. And anything else, when it gets closer and closer to the nucleus, is minus an increasing number. Okay? That's just a definition. So, now this is purely for a hydrogen electron, or the hydrogen atom. And so I'm asking you now, you have this equation here. We didn't do this the last time, didn't we? That was at the very end, wasn't it? Huh? No, we started it, but we didn't answer it. We started it, but we didn't answer it. Is that right? Good, okay. Switch transition in helium has the same wavelengths as 2 to 1 in hydrogen. 2 to 1 is this one here, 2 to 1. No, this is 2, and this is 1. I'm pointing here at the energy, because that's the question. Which transition in helium has the same wavelengths as 2 to 1 in hydrogen? So this is here, it's right here. This is this level to this level. No, level 2 to level 1, you go from here to here. So what would it be in helium to have the same energy levels, the same energies? So you just got to put it in and calculate it until you find it and give me the answer. Just use helium and put it in for n equals 1, for n equals 2, for n equals 3 if you find the same level. Okay? The level energy, not the same level energy. You caught it in time. Good timing. So the question is a 2-to-1 level, 4-to-1 or 4-to-2 level in helium plus? It's still a single atom system because helium has 2 electrons. We took 1 away, so we have 1 electron left, and we treat it as a single atom, a single electron system. Sorry. I have 2 programs running in the background, and they disturb that thing, okay? Oh, gee. So, let's see. It's going to display this. Okay, 4-to-2. That's pretty good. So you can calculate the energy levels of helium already and compare when the energy is the same. So the difference between these 2 levels got to be the same. So let's discuss this. I will discuss it for you. That way you don't have to go through all this stuff here. I got to close that program. I can't believe how slow this is. Okay. Oh, there it is. Okay. All right. So what is this here? This is our hydrogen, isn't it? No, that's not our hydrogen. Is it our hydrogen? No, that's not our hydrogen. This is our hydrogen. So this hydrogen level was minus, n equals 1 was minus R, and n equals 2 minus R fourth, okay? The ground level for helium is what? Helium is 2 is 4 divided by 1 squared is minus 4R. That's the ground state. Okay, minus 4R. You see any minus 4R here? No, I do see any minus 4. So that's not the right level. The next level is n equals 2. So this is minus 4 divided by 4. This is minus R. Minus R. So this is the same energy level. The first excited state, or the second quantum state for helium equals the ground state for hydrogen, for the hydrogen electron. So we have this one we found already. Now let's go for the n equals 3. This is minus 4 divided by 9 is minus 4/9 times the Rydberg constant. That's not it. So let's go n equals 4. So this is E4 then. N equals 4 is minus 4 divided by 4 to the square is 16. So this is 1/4, okay? This is minus R4. So this is level 2, energy level 2. You go from 4 to 2. You see the distance is the same, so the energy difference has to be the same, all right? So with this, you had the answer from 4 to 2, and just what I said, and this was the right answer as so many of you had. So I need to get a different computer when I have these programs open. Okay, now there's a very simple thing. If I ask you, you calculate for a spectrum. It goes from, the electron goes from level 4 to level 3 of a certain atom. Let's see, a 1 electron atom. So 4 is the initial level and final level is 3. Yeah? So delta E is minus C squared times R. That's a constant. For you, of course, you have to put the right C in there. Minus, or 1 times, come on, 1 over the final level squared, minus 1 over the initial level squared. Then you get that delta energy. You just did it exactly. You just subtract them from each other, and that's it. All right? That's just that you're not surprised if you see something like this. Oh, that's something totally different. No, it's not. It's the same thing. Okay. So let's talk about a little bit more about quantum numbers. Oh, I'm already here. Okay. So far, we know the electron in one dimension, how this would look like. All we can do is the energy level. We know that energy level. But fortunately or unfortunately, the world is three-dimensionally. So there's got to be, this orbital has to be reaching out somehow and has to have an orientation in space. So if you solve the Schrödinger equation for three-dimensional waves, you get a very interesting figures. And we never will do this, we're not solving the equation. You get we make it pictorial. We can depict the probability to find that electron in space. So we have learned about the first principal quantum number, or the principal quantum number, this is n. N equals 1, 2, 3, up to n equals n. And this gives you the energy. And you have seen that the total number of nodes, remember, is n minus 1. If you had n equals 2, that was a full wavelength, you have n minus 1, you have one node. All right? So, but now we need to somehow extend this three-dimensionally. So we need another quantum, we need a whole set of other quantum numbers to describe these orbitals in three-dimensional space. So the next quantum number is L, and these quantum numbers depend on each other. The next quantum number is L, we call angular momentum. Angular momentum, my God. Okay, angular momentum, and this goes from L equals 0 to 1 to 2 to 3 to 4 to 5 to 6 to n minus 1. Okay? If n is 1, what would be L? 0. Okay? If n equals 2, L can be 0 and 1. If n equals 3, L can be 0, 1, and 2. All right? So this gives you the shape and the number of angular nodes, and I'm just saying this is L. All right? So what does he mean with this? So we have the secret language again. When we talk about the angular momentum quantum number, if it's 0, we call that orbital an s orbital. Okay? When I say s orbital, you always know L equals 0. When I say p orbital, L equals 1. This gives you a certain shape. When I say d orbital, L equals 2. I don't say anything about the energy. I just say something about the shape. Okay? So we have s, p, d, and f orbitals. That would be L equals 3. That's as far as we're going to go in this class. All right? There are higher orbitals. I can go as much as you want. The wave function is unlimited, essentially. But it doesn't make any physical sense. So, and then we have another quantum number. So now they have a shape. S orbitals, they are radial symmetric. P orbitals, they look like a pendulum. And D orbitals look very weird, okay? So I can describe it to you. I will show you all this. Is the microphone okay? Yeah, okay, good. Can you hear me in the back? Can you hear me now? Okay, crank it up a little bit, please. Better? Good, thank you. So now we have the shape of the orbital. Now we're going to have direction. So it can go x, that would be this direction here. It can go y, would be this direction. And it can go c, would be this direction. So it has to be certain orientation in space. Not just a shape, but it has to have an orientation. Because they have to orient, these orbitals have to orient towards each other when we want to do binding. If the one electron orbital goes like this and the other one from the other molecule goes like in this direction, they never come together. They need to interfere with each other. These orbitals, they need to constructively interfere to bind. Okay? The orbital of one atom and the orbital of another atom, they need to interfere to bind. And this is only possible if they are looking at each other in space. And so this is why we need that quantum number, the magnetic number. It depends on L. The magnetic quantum number is from minus L, L minus 1, 0 to L, minus L minus 1 to 0 to L minus 1 to L. My God, what does that mean? Okay. What is, if I have n equals 1, L is 0, for an s orbital, what would be the magnetic quantum number? 0, okay? There is no orientation, obviously. If I have n equals 2, n is equals 2, then what p can be 0 and 1, okay? So let's look, if p is 1, what would be the magnetic quantum numbers? Minus 1, 0, and plus 1. That gives you 3 different orbitals. I'm going to get to you in a minute. Don't get confused, okay? You will get it. And many of you have gotten it already. That gives you the orientation in space. Now let's look at this a little bit more in detail. N equals 1, and this is all for a one-electron system, okay? This is not ion, this is atom, supposed to say. N equals 1, so L can only be 0. There is no L equals 1, yeah? L can only be 0. L is 0, that's S. We call this S, that orbital. Yeah? That comes from the German name S. When they did these experiments, they say sharp, principal, diffuse, and fundamental. That's where it comes from, SPDF. Forget it, okay? Just you need to know SPDF, all right? So and of course, they're more complex they are, the higher they go in energy, the higher you will be in energy. So that would be a 1s orbital. 1s, all right? M sub L would be 0. That would look like this. So the probability of finding that electron is anyway here in between. Actually, you only can give it to 90% probability. I explain this to you in a minute. That you find is somewhere in this space. And this is a 3-dimensional space, so what would look like this? A sphere, all right? And we put this plus here that shows you that the lobe of the wave is the positive or the negative. In order to do this, then you can see where the lobe is sometimes, yeah? Or the node is, all right? So it goes from positive to negative. There got to be a node. So that's the 1s. So how many nodes do we have? N minus 1, 0 nodes. There is no 0 node, this is just a sphere. So if you, for example, let's think about now let's say there's electron, we follow this electron with an extremely fast camera. Unfortunately, we can't do that. And we take every thousandth of a second, we take a snapshot. The electron will be here, 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 here. And we do this for an hour, okay? And then we superimpose all these pictures together. They're transparent, we put them on each other. You get exactly something like this. Or when you have a picture, I think it's a picture in your book, not a picture of beer, a baseball pitcher, okay? When you have a picture, and the picture, you have a good picture, he or she hits the strike zone, and the strike, I don't know, is it here, the strike zone, or is it here? Where's the strike zone? Okay, I don't go there, okay? All right. So the pitcher hits that strike zone, and the good pitcher hits it a lot in the real center of the strike zone. But of course, he's not perfect. He will hit it. He will hit it a lot here, but every now and then he will hit it here, and every time he misses too. That's the 10% of the probability. So to 90% of the probability, we can say that this electron we find here. It's darker here, so it's got to be higher probable to find it here, closer to the nucleus, and less probable to find it further out. And here we don't find it at all. So let's see n equals 2. So that's the principal quantum number is 2. What could be L? L could be 0. L could be 0, and with this, M sub L could be 0. Is that right? So this is a 2s orbital, because we have that number 2, and we call this then a 2s orbital. So how would that look? Would look like this. What's this here? There is a radial node. A radial node. If you look here, the number of total nodes is n minus 1. N equals 2. Minus 1 is 1, so you can get 1 node. And since it's an s orbital, it has to be a radial shape, a spherical shape. Now, there is these Russian dolls, I don't know what the names is called, but you can put them into each other, and you can put all these into each other. Now, think of them, they would be spheres, okay? Not dolls, but spheres, colored spheres. And you put one, and you put the second one in. So there's the space in between the two spheres. This is where your node is. There's exactly how this would look like. You have one, and then the second one, okay? So you have one node. Now, how many nodes would you have if n would be 3 and L would be 0? How many nodes would you have? 2 radial nodes, okay? That would be then the orbital, what would that be? The 3s orbital, all right? So this is how we name it, and how we can say this is a 3s orbital, and we know that they are becoming higher and higher in energy. 1s is lower in energy than 2s, and 2s is lower in energy than 3s. Okay? We've seen this here in the one-dimensional case. So there it is. That is the probability distribution here for the hydrogen 1s orbital. And it's not in three-dimensional space because it would have to come out here. Unfortunately, I don't have a three-dimensional screen. And you don't have these glasses on because I would have to have 2 colors in order for you to see. You know that about this already. So this is then here the probability density. So if this is the probability of finding, that's the density if I have the nucleus here. If I go away from the nucleus, so it's rather dense close to the nucleus, and then it gets less and less and less dense. So that's exactly what this does here. It gets less and less dense, and then at the end, it goes asymptotically here. It will never go to 0. And this is why you can give the probability only to 90%. You have to cut it off somewhere, and this will be the rest of the 10%. All right? So this was simple. That was the s orbitals, Now here I have a cut through them, but I just explained to you. This here would be at the 1s, there is no node. 2s, there is 1 node. 3s, there is 2 nodes, 1, 2. And this would be the radial distribution function. So it goes out here like this. But then here, this one goes to 0 because it goes from inside to the outside and then becomes 0 here. And then it goes up again in energy. And then it goes asymptotically along the r-axis. R is the distance from the nucleus. And this would be for the 3s. So it has the high density here. Then it goes down to 0. That's this here. Then it goes up again, that's this here. Then it goes down to 0, that's this here. And then goes up and asymptotically along the r-axis. And from the outside, they all look the same. They're just larger. But you need to know that there are these nodes inside. And the number of nodes is defined, the number of radial nodes is defined by the quantum number. So we had n equals 2 and L equals 0. That was the S. But we can have also n equals 2 and L equals 1. Isn't that right? With this, if L has a number, it's not 0, what happens to m sub L? M sub L goes from minus L to 0 to plus L. All right? So m sub L would be then minus 1, 0, and 1. This would give us 3 orientations. This darn thing here, that's a p orbital. We call this a p orbital then, if n equals 2. No, if L equals 1, it's a p orbital. I'm sorry. If L equals 1, it's a p orbital. N equals 2, L equals 1, it's a p orbital. So p orbitals look like this. So this is minus 1 and plus 1. So it goes, the one, and we in your book, I think the x-axis goes to the front, the y-axis to the side, and the x to the front, the y to the side, and the c-axis up and down, all right? It really doesn't matter. People depict this always, as long as we define what axis we mean, all right? So this would be a px orbital, this would be a py orbital, and then we would have a pz orbital. That would be a pz. So this would point upwards here, has a node here. These are called now, what are these nodes called? They are angular nodes, okay? Angular nodes. So the number of angular nodes is L. So how many angular nodes can you have? 3. No, one angular node. You have three different orbitals. So there's one angular node here, one angular node here, and one angular node there. So it goes through 0 here. So now you understand if you have p orbital binding, and there are two p orbitals, they have to point at each other. So it's very unlikely that this one binds with this one. If it doesn't overlap, it has to overlap. Okay? So if this one, let's see, if two of those you have, they are pointed at each other from different atoms, then they will bind, because they can overlap here constructively and destructively, and we get to this in more detail. So if you have n equals 3, you can have L equals 0, 1, 2, and then you have S, P, and d orbitals, because L equals 2. So how many, we have established the p orbitals, we have 3 p orbitals. How many d orbitals would you have? How many? 5. How do we get to that? L is minus 2, minus 1, 0, plus 1, plus 2, and that's it. Yeah? Okay? So we get to this also in a minute. So this is the representation. Again, if you do the start model, if you take the snapshot of the electron and then superimpose these snapshots, you get something like this, a probability distribution, the representation of the 2p orbital. We cut through it, okay? So you see that there's this node here, it's an angular node, there's nothing going on here, and here the highest density is here, and here close to the nucleus, and then it gets less and less dense here, right? And with this we can describe the probability of finding that electron to 90% about, yeah? Not to 100%. And we don't really know where it is because of our uncertainty relationship. It's somewhere here. It's highly likely that it's more here than here, but we can't pinpoint it. That's the problem, or that's the charm of it. Now, if we, and these are very, very complex orbitals. For example, a 3p orbital, it has several other nodes, and this is, for example, a conical node. We don't go into that. There are some very complex orbitals, and I'm not going to quiz you on these things. So let's go through it in summary. We have n equals 1. That means L equals 0. With this at 0, L equals 0, S. All right? So that is the n is the first quantum level, quantum number. So that's the 1s orbital. And m sub L is 0 because it's spherical. It's oriented to everything in space. So it doesn't have an orientation. X, Y, and Z is the same orientation. It's a sphere in space. All right? So the next one, quantum level, is n equals 2. You can have L equals 0. That means S. L equals 0, S. So that is then the 2s orbital, and we know now that the 1s orbital is lower than the 2s orbital. All right? But I can have also another quantum number. L can be 1, and with this, I know L equals 1, p orbital, right? But now I have L. I go from minus L to 0 to plus L is m sub L. With this, I have now the orientation. That magnetic quantum number gives you the orientation in space. Now you have 1, 2, 3 different orientations, X, Y, and Z. All right? So we have 3 orbitals because of this. Now we go to main quantum number 3. You have L equals 0, S. Here's the 3s orbital, and that's it. Radial, symmetric. It has no other orientation. So there's one orbital, but I ask you, how many nodes does this have? How many nodes? 2. And what are these nodes? Radial nodes, exactly. So, but we can also have, if n equals 2, L can be 1 and 2. So if it's 1, L equals 1, P. Okay, P orbital. Always L equals 1, P orbital. So that's then the 3p orbital. And since L equals 1, we have minus 1 is m sub L, 0, and 1. So we have 3 p orbitals. As we have 3 2p orbitals, we have also 3 3p orbitals. They are different in energy. because we're on a different energetic level. But now, since we have n equals 3, we have L equals 2 d orbitals, sp-d orbitals. If you have C, L equals 2 d orbitals. So you have 3 d orbitals. So L goes from minus L, minus 2, minus 1, 0, 1, 2. So you have 5 different orientations in space. With this, you have 5 d orbitals, all right? And they are higher in energy than these other ones, these lower. Now let's go to main quantum number 4. L equals 0, one possibility, S. Quantum level 4, 4s. No L equals 0, so there can't be no m sub L, 1 orbital, 1 4s orbital. The other possibilities is L is 1, S, P is 1, D is 2, and 3 is F. S, P, D, F. These are the 4 orbitals you need to know, okay? Nothing else. And you don't need to know the shape exactly, but you need to sort of recognize this must be a p orbital, this must be a d orbital, it must be an f orbital. They become more and more complex. And with this, you have then, goes from m sub L is minus L, is minus 3, minus 2, minus 1, 0, 1, 2, 3. So we have 7 f orbitals, 7 of those, okay? So with these orbitals are nearly enough to fill all the electrons of the periodic system in there. All right? Actually, we need the 5f, but that's a different story. All right. Let's see. So this is the 3d orbital. See, there's 2 planes, 2 angular nodes. This would be the 3d xy, and so on. They have these funny shapes, all right? But they look like this. And this is how the 5d orbitals look. Like this is looks like it ate too much here. And that's the dc squared here, okay? And the dx squared minus y squared, dxy, dxc, and and this here? Isn't that the same as this here? Twice. Okay, there's a square there or something? Anyhow, good. So you see, they're different in shape, all right? Have a close look. This is how d orbitals look like. And now we're going to come to f orbitals. They look even more complex because they're higher in energy, much higher wave functions. You need much more waves, many more waves to model this, solutions to that wave function. Okay? So that's the 5f, and I'm not going to go into the detail of this. Let me ask you a question. It's a simple question, but this is a p orbital. Don't get fooled, okay? I ask you, just in the simple explanation which I gave you about radial nodes and angular nodes, which has the most radial nodes? The 4f, the 3d, or the 2s? Look at it very simply. Okay. And there's no way that we can buy a new computer with the current financial situation. Can you believe this? Huh? It will come up eventually. I have these 2 huge programs running in the background because I want to show you a demonstration of this. Okay, there we go. See how fast it registers you? Okay, thank you. I'm talking about radial nodes. So what I told you so far, only certain orbitals have radial nodes. It's not 100% correct, because if you go to the very different called ones, there are some radial nodes, but you cannot know that. I barely know that. Thank you. All right. Woohoo. Okay. Okay. By the definition I gave you, you only can have radial nodes if you're spherical. Okay? That's the definition I gave to you. Yeah. The others that are not radial and have nodes, let's assume they are angular nodes. All right? If you have n equals 1, that's the number of total nodes. But would you have angular nodes if n equal? No, never mind. Never mind. Radial, what does radial mean? It goes around like this in a radius, okay? Now why don't you discuss this a little bit and think about it again? Oh. But it bounced up. Come on, click in. Can you click for the gentleman there, please? Yeah, just click. He's here. Does biology prohibit him to be here? Yes. There we go. The simple definition I gave you, this is correct. So what's the solution? The solution is the total nodes are n minus 1. So if you have the number, L is the number of angular nodes, and so S you have 0 angular nodes, D you have 2, and F you have 3, okay? And so with this, it has to be S is 0 angular nodes, and the question was what has the largest number of radial nodes? Isn't that right? That was the question. There's only one that has radial nodes, that's the 2S. So how many radial nodes if I have a 10S? How many radial nodes would you have? 9, okay, good, all righty. Now, let's see if I can show you this. We're gonna play a little bit here, if I ever get to this. I'm going to show you these orbitals now, and we do a real-time calculation. I got to close as much as I can, and then we're going to go here. Eventually, there will be a question still. Okay. What is open here? Let's look at this here. I mean, I can't work with this computer. It's so slow. I mean, give me a second. Applet is open in a separate window, okay? So this is this here then. I can't believe this. Okay. Next time I bring my own computer. I mean, this is terrible. See that? How it's not loading at all here. Okay. Let's see. There it is. Sort of. Okay. N equals 1. It's a neat little thing here. You can, let's see, let's put that x around here where, 1 second. Got to put that x here. There it is. Now I'm having it right. So x and y. The x goes to the front here, the y to the side, so I'm going to make it a little bit from the side. So let's go for n equals 1. L equals 0, okay? It's a 1s here. That's real-time calculation, actually. N equals 2, you have L equals 0, that's the s, or you have the p. That's, for example, the pc, it goes in this direction. Then you have the px, it goes in this direction. You see the axis there? See the axis right here goes in this direction. And the py in this direction. You see the py goes in this direction. So you see, these are called what? Angular nodes. Now let's look at the n equals 3. So L equals 0. There's, how many nodes do we have? 2. There's got to be one here, and one here. See, and it's changing. The resolution is not too great. Let's get the resolution a little better. Okay. Now, we have L equals 1. That would be the 3p electron. Look at those guys. Okay. The 3pz, that goes into the z direction. This goes in the x direction. And this goes in the y direction. This is how they look here. So there are nodes here. You see that? There are nodes here and here. And now let's look at the next one. N equals 4. That would be the 4s. So that should be 1, 2, where's the third? 1, 2, 3 nodes. You see it? And now let's go to the p. We should have 3 p's. Three directions. That's the 4pz, 4py, and 4pz, 4px, and 4py, okay? And then, what else do we have here? We have the d orbitals. Oh my God, look at those. So we have 5 of those. The dz squared, then the dxz, then the dyz, and the dx squared minus y squared. And these are real calculations. So, and the 4dx, so how many d orbitals are those? 5, that's what you need to know. 5 d orbitals. Now let's go to the f orbitals. There's got to be some f orbitals because L can be 3 also. So L equals 3 f orbitals. Okay? So we have 7 of those. This is, let's see, this is the 4f3, fz3. This is the next one. The next one. Look at those babies. The next one, this is the 5th, 6th, and 7th. And you can also rotate them now. Look at this. See the nodes here? See all the nodes? Here? These are angular nodes here. All right? So I don't expect to reproduce this, but you need to know that there are 7 f electrons and 5 d electrons and 3 p electrons, 3 orbitals, not electrons, orbitals. I see you on Wednesday tomorrow at 5 to 7. There's review. Greg Dellinger does review here. There is a midterm on Monday, okay? You should have gotten mail, 6:30, I think.
So, and